All right, so now we're going to spend a little bit more time doing stability analysis of the parabolic, the explicit method for a parabolic equation. And previously we had done this by looking at the spectral radius of the linear system. So now we're going to take a different approach, which is to do essentially a Fourier expansion and to see which modes are supported by the equations. Okay, so we're going to do stability analysis. But by using the Fourier method. So let me just remind you that we're considering a discretization of a parabolic system. In particular, we're looking at the heat equation. Okay. So let's recall the heat equation. Okay, which looks something like uxx is equal to ut. All right, and you would expect that the solutions which are supported, it's like by the numerical method, are related in some way, shape, or form. It's like to the solutions of the actual equation itself. Okay, so you can observe that. So observe that the solution of the heat equation well, let me sort of rephrase that so that their A solution is given by the following. So u x of t is equal to e to the minus pi squared t sine pi x. Okay, so what that sort of is looks like, if you will, is an exponential in the time direction and a sinusoidal term, it's like in the spatial direction. So what we're going to do in some sense is to look at how things which are exponential in time, it's like, but again, it's like sinusoidal, it's like in space, behave under discretization. Okay, so this motivates. So this motivates sort of looking at sort of the modes of the form. Let's call that Vjn, which is the form e to the I j beta h. Sorry. Okay, and then e to the n lambda k. All right, where I is sort of the square root minus 1, right? So again, it's like the idea is to have something which is exponential in time, and then sinusoidal, it's like in space. And of course, it's like you can write sines and cosines, it's like in terms of, it's like exponentials of imaginary terms, right? Which is sort of what you have here, and then there's an exponential term here, okay? So this is, going to play the role of the sine and cosines, and this is going to play the role of the exponentials. Okay. So, given sort of a suitable choice of lambda, right, we look at the solution as t goes to infinity, right, or as n goes to infinity. Okay, so basically, if you will, it's like this is the part which is the spatial, sorry, the temporal, it's like behavior, right? And you're trying to look at, again, what happens, it's like whether there's blow up, Okay, um, so and then this is sort of the thing which is sort of the sine and cosine term. It's like that norm is bounded, so the norm of this numerical solution is associated with the growth of this term here, right? So this depends on sort of e to the n lambda k, right? Which is of course just e to the lambda k to the nth power. Okay, so if the norm of e to the lambda k is greater than 1, then this solution will diverge. It's like over time, right? Is unbounded. Sorry, unbounded. As time increases. Okay, so that's the thing to keep in mind here. All right. So we're going to, essentially what we're going to do basically is we're going to substitute, it's like an expression of this form into the defining equation for the explicit method and then see what happens to it. All right, so that's basically what's going to happen. All right. So the defining equation, it's like for the method, right? So let's see. So the equation has the form, it's like Vij plus 1 is equal to S Vi minus 1j, right, plus 1 minus 2S Vij plus S Vi plus 1j, right? Where S is equal to k over h squared. Okay. So what you're going to do is you're going to substitute this term into this expression here, and then see what happens. Okay, and in particular, we're going to see what values of lambda are supported. It's like by an equation of this form, right? Okay. So you substitute. Substitute star into sort of the defining equation for our explicit discretization of the heat equation. And then to see what happens. Okay. So when you do that, what you end up getting is the following, right? You get e to the I j beta h, e to the n plus 1. Okay, I should make the remark that what happened here was that instead of I and j as the indices, we've changed to j and n. And the reason for this is because, of course, I here is going to be the square root of minus 1. So this term here, which I have here, right, lambda k, so this you should read as v j n plus 1, right? So every time you see an I call it a j. Every time I see a j, I call it an n plus 1. So I'll just write it down. So v j n plus 1 is equal to s v j minus 1 n plus 1 minus 2s v jn plus s v j plus 1 n. Okay, so that's just reindexing the defining equation so that there isn't this notational conflict with the square root of minus 1. Okay, all right. So I'm just actually going to rewrite this here, right? So Vjn is equal to e to the ij beta h e to the n lambda h. And that was the start equation here. Okay, all right. So I'm just rewriting this in this way. And then now I want to substitute this into these terms here. Okay, so this is going to be s e to the I j minus 1 beta h e to the n lambda h. So it should again be clear that this term here is just v j minus 1n, right? And so I keep going, 1 minus 2s e to the I beta ij beta h e to the n lambda h, right? So n lambda k. Yes, k here. K here. All right, plus s e to the I j plus 1 beta h e to the n lambda k. Okay, right, again, yeah, so I first took the defining equation again. It's like for the explicit method for the parabolic sort of the discretization of the equation, re-indexed it, and then used this form of the solution and substituted it to give you this here. Okay, so once you do that, it's like you can sort of basically divide throughout, it's like by this factor and see what happens. So dividing by e to the I j beta h e to the n lambda k throughout yields the following. Okay, you get e to the lambda k is equal to s e to the minus I beta h, right? Plus 1 minus 2s plus s e to the I beta h. Okay? All right, and recall it's like what we're aiming for is to see what happens to this e to the lambda h term, in particular whether the norm is greater than or less than 1. Okay? All right, so now we have an expression for what we're looking for, which is good. Okay, so this is equal to 2s cosine, and then these plus and minus, I mean, it's like the exponents is the plus and minus I beta h terms. It's like that's going to give you a trigonometric function, which is just cosine beta h, right? Right, 2 times cosine beta h, right? Plus 1 minus 2s. Okay, so I can simplify this further. This is 1 minus 2s, 1 minus cosine beta h, and then rewriting this gives me 1 minus 4s sine squared beta h over 2. Okay, yep. And sometimes it's easier, it's like to, if you don't remember your trigonometric formulas, it's like it's sometimes easier to manipulate it at the level of the exponentials of complex numbers. Okay, all right, so yes. So we want, if you recall, that the norm of e to the lambda k be less than 1. Okay. So it's sort of clear, it's like that this term is less than 1 already, right? It's less than or equal to 1, sorry, right? So we know that e to the lambda k, right, is less than or equal to 1, so long as beta is real, right? So if beta is real. Okay. So what you need is for sort of the thing where you take away, it's like the absolute values with, and you put a minus sign there. So we want to, so for stability, we want that e to the lambda k is greater than or equal to minus 1. Okay. So either lambda k is greater than or equal to 1 and either lambda k is less than or equal to 1, it's like then the norm of this is going to be less than or equal to 1. Okay, so, all right, so we want that 1 minus 4s sine squared beta h over 2, right, is greater than or equal to minus 1. All right, and that gives me that s sine squared beta h over 2 is less than or equal to 1/2. Okay. All right. And then because sine squared beta h over 2 can be close to 0, can be close to 1. Right, we want that s itself, right, should be less than or equal to 1/2 for stability. Okay, all right, which was sort of the exact same stability condition we had derived before. It's like by looking at the spectral radius of the linear system. Okay, so this is another way of doing it, and you know, this is in some sense easier because you don't have to compute a spectral radius it's like of a matrix, which can oftentimes be difficult, right? Unless the matrix has a particularly nice form. So here it's like it's a little bit simpler, right? So, but whatever method you're more comfortable with is fine. Yeah. So let me just stop here for now.